Okay. So I'm the presenter today. So if something is not going well, just alert me. All right. Um, yeah. Good morning, or good afternoon, or good evening, everyone. Um, and today I am going to talk about the sustainability assessment of technologies to remediate groundwater contaminated with PFAS. So, as you all know, this is our geoenvironmental engineering webinar series. Um, I want everyone to note down this link at the bottom. That's where you will find all the details about these webinars and also link to the YouTube channel. So I think that, just keep this, the link handy. So as I said, like we have been having webinars. We have over 70 webinars so far. So all of them are recorded. They are available. So it's going to be a great resource for anybody who wants to enrich their background in geoenvironmental engineering. And then, so this is the last seminar for this spring. And maybe we will take a break during the summer, and we will resume in the fall on different topics and different speakers. All right. So just to introduce myself, I'm from Chicago. Many of you may have already visited Chicago. So, I'm talking about international attendees. Chicago is a beautiful place, so I highly recommend everyone to visit Chicago. And just regarding my research, I am in charge of these two labs: Sustainable Engineering Research Lab and Geotechnical and Geoenvironmental Engineering Lab. So I do a lot of research on environmental remediation of soils, sediments, groundwater, and stormwater. Um, I also do research on waste management and landfill engineering. So these two, I call it as a geoenvironmental engineering. Uh, I also work on life cycle assessment, sustainable and resilient engineering. This is kind of a very broad area. In this, I am more interested in quantifying the sustainability and resiliency, and then applying that kind of a framework to various engineering applications. So my master's and PhD background is in geotechnical engineering. I worked for 3 years in industry before joining the university. I know a lot of geotechnical practices, design of landfills, and uh, design of remediation systems. So you can go to this website. You can find more information about my lab and my research. So whatever research we have done over the past 25, 26 years, and they all summarized in these 4 books and many journal papers and many conference papers. Again, you can go to this link. You should be able to find all the information. So I just want to take this opportunity to say a couple of things about my research philosophy. So what we do is we identify a real world problem, um, and we try to come up with a hypothesis on potential solution, and then we try to test that one in bench scale testing. Basically, these are small scale testing, which is very easy to test, does not take much time and much resources. And if that shows the positive results, then we scale up and do large scale lab experiments. Experiments are good because you can control different variables and understand the fundamentals. And then once you understand the fundamentals, you can incorporate those into mathematical models. And then you can use those mathematical models for scaling up for field applications. And then in our research, we also, whatever we have done in the lab and whatever we have done modeling, and we try to design the field scale systems, and we try to go out do some pilot scale field testing to see if what we proposed is going to work in the field conditions or not, because you cannot simulate all the field conditions in the lab. So it's very important to go out to the lab and see whatever you found in the lab can be translated to the field conditions or not. So we do, lab testing, modeling, and the field testing. So that's our research methodologies. And then our goal is overall to advance the fundamentals and ultimately to develop practical solutions to the real world problem. So um, we really aim to solve the real world problem. So we tailor our research towards that. Not just do some research and write some papers. So I do a lot of experimental work. This is my lab. Again, this is one of the problems for every researchers, to have the research infrastructure to be able to do good research. Good research. So I always show this slide. Over 25 years, I have the privilege of working with many talented students and visiting scholars from all over the world. And whatever I have accomplished is due to the hard work of all these students. So I always thankful to them. So that's kind of a brief background of myself. Now let's come to the presentation. So this presentation is about sustainability and groundwater remediation. So first of all, I wanted to talk about sustainability. And as I mentioned, I'm more interested in sustainability analytics, how to quantify the sustainability. I will show you this general methodology that I follow to quantify the sustainability of any engineering project. And then I'll show you, this case study of applying this sustainability framework to assess which methods are sustainable to remediate groundwater that is contaminated with PFAS. So I will talk about what is PFAS also a little later. So the first part is about general sustainability, and second part is how to apply that to remediate groundwater contaminated with PFAS. So then the closing comments. So the case study that I'm going to talk about, that groundwater that is contaminated with PFAS, that work was done by graduate students here, and we have a publication on this one. So I just want to acknowledge the help of graduate students for doing this work. So let's get to quantifying the sustainability. So the problem that we have now is in any engineering projects, we don't consider the sustainability. So what we do right now is we look at the codes and regulatory requirements, and we do the technical design for safety. And then we look at, which option is easy to construct, which one costs less, which one takes the less time. So this has been the standard engineering practice for many, many years, even today. But as I said, we don't consider the sustainability, we don't consider the life cycle thinking, we don't consider the resiliency. So if we consider these additional factors, then we could be, coming up with a very innovative solutions. So that are effective, safe, and also economical. So that's why now, sustainability and resiliency are becoming very important. And you must have heard about sustainability and resiliency for a long, long time. So what is sustainability? This is the definition that people use. Burnland Commission definition: development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So this is kind of definition that people use. It's a nice definition, very brief and very powerful. So people are talking about sustainability these days because of this global climate change that is occurring due to greenhouse gas emissions. And as a result of climate change, we are seeing a lot of extreme events, floods, droughts, wildfires. So these are impacting current generations and future generations too. So that, as I said, climate change is due to greenhouse gases. Greenhouse gases are basically carbon dioxide, methane, and nitrous oxide, and they have been increasing significantly. We have a lot of greenhouse gases already in the atmosphere, and we are emitting more and more. And as a result, we are going to see these extreme events happening more and more into the future. So the global climate is changing. As you see, the average global temperature has been increasing. So these climate change impacts are evident everywhere, but they're not uniform. So some places it's extremely dry, some places extremely cold, a lot of flooding, a lot of hurricanes, tornadoes, ice melt, a lot of hunger, air pollution, wildfires. All these things are contributed to the climate change. And even in India, you have been seeing some places. It's very dry. Some places, a lot of flooding. Um, that was not that didn't happen in the past. So now, you know, places that are not known for flooding are severely being flooded, and a lot of damage that is happening. So in addition to the climate change, we have to worry about sustainability because of exploding population growth. And if the population is increasing, you're going to see some impacts of that, right? So the population is going um, at an exponential rate. And if you have more people, you need more natural resources. Um, and people are generating a lot of waste, per person waste. I see how much you throw out, every day. So multiplied by the number of people. So if the number of people are increasing, then the waste generation is going to increase. So increased pollution is happening, and damage to ecosystem, loss of biodiversity, urban sprawl, and economic disparities are growing, and social injustice issues are growing. So these are kind of some issues associated with the exploding population growth. So, business as usual is not going to solve these problems. So these problems are going to become more and more if we don't take them serious and start addressing doing things differently. So the sustainability can be addressed at different scales. So global scales, like different countries are having treaties to control the greenhouse gases. National scale, it could be, so each country could be coming up with a policy, for example, energy going into the cutting down the fossil fuels and going into the renewables. So that kind of a national level effort. Regional scale effect, it can be done regionally, like a whole watershed area. If you're trying to um, address the water resources or flood management or stormwater systems like that. Or it could be done at business or institutional scale. For example, you could have a eco-industrial park, or you could have a university campus itself, thinking about sustainable campus. And then a last one is the sustainable technological scale, because this is where engineers, can address, engineers deal with materials, designs, products, and systems in their jobs. So now looking through the lens of sustainability, what they have been doing. As I mentioned, we cannot do, same way that we have been doing. So you just ask the question of, whatever I'm doing, is it sustainable? So maybe that will give ideas on doing some things different. So So I want to do something for sustainability, but the sustainability definition is so broad, right? So we need a functional definition. So there are many functional definitions. One functional definition is given by American Society of Civil Engineers. So it starts with a set of environmental, economic, and social conditions that's known as the triple bottom line, in which all of society has the capacity and opportunity to maintain and improve its quality of life indefinitely without degrading the quantity, quality, or the availability of natural, economic, and social resources. So this is a little bit wordy, but it really gives you the practical way of addressing the sustainability. So the main thing here is the triple bottom line. And this kind of a functional definition can be applied at different scales, even at taking down to the project scale. So what we are talking about is this triple bottom line. Triple bottom line is all about environmental, economic, and social aspects. We need to consider these. In addition to whatever the technical design that we are doing, we don't want to compromise the safety, right? We don't want to. We want it to perform the function, but you know we need to, if we have a different options, we need to consider these triple bottom line aspects and see, we can reduce the negative aspects and increase the positive aspects. So then it makes your technical design more, or technical option more sustainable. So you need to have indicators. Okay, when I say I want to address the environmental issues and economic issues, social issues associated with my project, to make it more sustainable, then you need to have indicators. You need to define the indicators. So what kind of environmental issues that I should consider? What kind of economic issues I should consider? What kind of social issues I need to consider? So you need to define the indicators. So once you have indicators, we have to be careful when you uh, define the indicators, because I like to quantify sustainability. So all the indicators should be quantifiable. So that's called metrics. You need to be able to put the numbers associated with those indicators. So once you define indicators that could have metrics, then you need to have tools to calculate those metrics. So this is very important from quantifying the sustainability point of view. Let's say environmental sustainability. So what kind of indicators that I could have? Energy, right? I could calculate how much energy is involved in the manufacturing the material, for example, or the entire structure, for example. You can calculate carbon footprint or greenhouse gases. And you can also calculate the smog, acidification, carcinogens, non-carcinogens, eutrophication. So these are all the indicators that can actually quantify it, and and you can have numbers associated with these indicators. There are metrics for all these things. As I said, you can have numbers, and also there are tools that have been developed. You could have specific tools. For example, in environmental remediation, we use SAFA or SiteWise. So those are the tools that are specifically developed for remediation purposes. But if you don't have a specific tool, a general methodology that can be used is called life cycle assessment, LCA. So LCA is, it's a standardized methodology. So ISO 14040 is the standard method. So basically, it's a compilation and evaluation of the inputs, outputs, and the potential environmental impacts of a product system throughout its life cycle. So we say product design, product system, but it can be applied to any just a material or a design, and whatever you're dealing with. So basically, inside you see the different processes, or like we call it life cycle stages of a project. And then what are the inputs that are required, raw materials, energy that is required. and you are getting whatever you aim to obtain by your process or design. But in the process, you're going to have these environmental emissions. So you could have atmospheric emissions, waterborne emissions, or solid emissions. So, what we are interested from sustainability point of view is, okay, if we give the raw materials and energy and go through these processes, we are producing what we want, but, in the process, we are having these environmental emissions. So we want to quantify these environmental emissions from the sustainability point of view. So this ISO standard is commonly used, and it has 4 phases. These are the goal and scope, life cycle inventory, life cycle impact assessment, and then interpretation of the results. So anytime anybody does the LCA, they follow these 4 standard phases and present the results. So that's environmental sustainability. The economic sustainability, again, you need to have indicators. Direct costs, like raw materials, transportation, labor, these are kind of engineering costs that you have. In addition to that, you need to think about indirect costs, like, for example, social cost of carbon. So you're emitting so much of carbon, greenhouse gases. What is the cost of that? So there's a US EPA report that tells you, how much is the cost per pound. Basically, what it takes to fix the problems of greenhouse gases in terms of the monetary terms, right? So you can also monetize other environmental impacts. So those are like indirect costs, because you are emitting this environmental. You're having these environmental emissions. So what are the costs associated with fixing the problems that emissions would cause, right? And then you could have a direct benefits. For example, if you're constructing a building, but if the building is going to be used for an office, how many people are going to be employed? That's kind of a financial benefit of the project, right? So a lot of times we look at only the construction costs, but we don't look at, direct benefits of that. You could have a indirect benefits, if you build something and if the surrounding real estate value has increased. So that's a indirect benefit of your project. So direct costs are easy to calculate, but indirect costs, there's some good handle on that one. The direct benefits and indirect benefits, they are a little bit complicated, and it depends upon the project that you're dealing with. So there are no standardized methods for that one. But you can use the life cycle costing or cost benefit analysis, and in LCA you can use a stepwise 2006. So you need to put a little bit of effort in terms of calculating these economic indicators. The other one is the third, in the triple bottom line, third aspect is the social sustainability. And then here, it's challenging to define the indicators that can be quantified. You're talking about people, how your project is going to be helping the, people who are going to be affected by the project. So as an individual or as a community, right? So how do we pick the indicators that can say, this project is going to be somewhat beneficial or not so beneficial, but how do we even quantify those indicators? So here are the potential indicators. For example, population growth rate, that's kind of a little bit broader. You can see all these student graduation rates, homeless households, So basically, these are all will give you an idea about the quality of life that people have in that area and how your project could impact all these things, right? So, but how do you, quantify these things? So it's very difficult to quantify. You don't have tools to quantify. But I developed a tool called Social Sustainability Evaluation Matrix in 2013. And in this one, it's kind of a rating tool wherein you can consider how an individual could be affected, how the community could be affected, how a community's environmental situation is going to be affected, how community's economic situation is going to be affected. So you have these categories, and then under each category, you have some key areas, and then based on the specific project and specific location that you're looking at it, you can assign some ratings, and you can quantify that one. So to summarize, basically, sustainability can be quantified using this triple bottom line approach. So you have environmental indicators, you have economic indicators, and you have a social indicators. All of them are in all of them have metrics, and then we could calculate those metrics. So as I said, we really need to think about life cycle. A lot of times engineers think about construction and the maintenance. Those are the only things, right? They design and they have construction contract awarded, and contractor will bring the materials and build it, and then you have operations. But actually, for sustainability assessments, you need to look at resource extraction, going back into mining. What are the things that you need to manufacture the materials? For example, I need cement, or I need steel, right, for your typical civil engineering construction. Or if I am needing a chemical for my remediation process. So the manufacturing of the chemical. So what resources you need for that one? What raw materials you need for those things? And then manufacturing those materials, right? So that's where a lot of impacts will come, the material manufacturing. For example, manufacturing of the cement, or preparation of the concrete. So those will, manufacturing of the steel, that will emit a lot of environmental emissions associated with that one. And then you transport them and then use it at the site, and then maintenance. Then you have to also look at demolition, and then how much of it is going to be recycled, right, or sent into the landfill. All these things have to be considered. So at each life cycle stage, you have to look at environmental impacts, economic impacts, and social impacts. So you have to combine all of them to get overall sustainability. You can do the sustainability assessment only for a particular life cycle stage, but that does not really give a really good overall sustainability aspects. So in an ideal sense, you need to consider the entire life cycle of the project, and then for each life cycle stage, you calculate these environmental impacts, economic and social impacts, and then you combine all of them to get overall project sustainability. So that's what you can do. These are the life cycle stages, as I said: raw material acquisition, material manufacturing, transportation, construction, operation and maintenance, reuse, disposal. So these are all the life cycle stages. For each life cycle stage, you apply the triple bottom line. You calculate environmental, economic, and social impact. So you will have a bunch of environmental indicators, bunch of social indicators, bunch of so these are social indicators, and you have economic indicators. So in a spreadsheet, you may have a lot of these indicators, maybe 30, 20, 30, 40, whatever, depending upon how comprehensive your project is. And then when you look at those indicator values, consistently, you will not have one option having all the positive results and other option having negative results. So you will always see the mixed results. So when you have that kind of mixed results, how can you make a judgment, right? So it's very hard. So, what we do is we use some multi-criteria decision analysis framework, and combine all those indicators, and then calculate one value, sustainability index. And if we have a sustainability index, then you can apply the same framework for different options. You get a sustainability index for each option, and then see which option is better. Or if you are just looking at only one thing, you can look at the sustainability index. Okay, this is too low. I want to make it more sustainable. So you can evaluate where the negative impacts are coming, and then go and focus on that aspect and see if you can do something different to make it more, favorable, and then improve the sustainability index. So you can optimize the given design that you have, or if you have alternative designs, you can see which one is more sustainable. So basically, this whole thing involves defining your technical design or design alternatives, and coming up with the requirements and criteria and indicators. And sometimes we can apply the weighing factors for those requirements, criteria, and indicators. And then what we do in this, this multi-criteria addition analysis is all the indicators have different units. For example, all the economic indicators are in dollar terms. All the social aspects are in the ratings, and you have environmental impacts with different units for different indicators. So we convert all those things into, using the value function. We we normalize it between the values of 0 and 1. And then we use all of that to calculate the sustainability index. And then once you have a sustainability index, you can make the decisions. Now all the indicators are probably not of equal importance. So if you want to apply weighing factors, you need to do it in different ways. But one of the most common way of defining the weighing factors is this analytical hierarchy process, wherein you compare all the indicators, comparing to itself versus comparing to the others, how important it is. So you're considering one indicator, how that indicator is importance of that indicator compared to the other indicators. So we use this kind of a rating system. This is kind of a standard SATI scale. So we ask this question, okay, the indicator that you're looking at, is it equally important to other ones, or slightly more important, much more important, absolutely more important? And we assign these scores, and then we calculate the weighing factors. So the point I'm trying to say is, if you want to consider the weightages for different indicators, there's a rational methodology that you can follow to achieve that. So basically, you have indicators, environmental indicators, economic indicators, social indicators. You can come up with the weighing factors for those things. And then you can normalize all those values by using the value functions. And then you can also use the criteria and apply the weighing factors and requirements. You have weighing factors. So these normalized indicator values multiplied by the weighing factors will give you this criteria value. And then you take the criteria value and apply the weighing factor, you get the requirement value. And then at the end, the criteria value, and then at the end you get the final value. So this is the this whole methodology. If it is confusing, look at this paper. This has all the details about what I've been talking about. Okay. So that's how we basically, at the end of our framework, we get sustainability index. And higher the sustainability index, it is more sustainable, considering all the triple bottom line aspects. As I said, first thing what we have to do is we have to do the technical design that can perform to meet your performance requirements, right? So after that, so if you have multiple options, which one is more sustainable, so you can apply this sustainability framework. But the one which has a high sustainability index would be considered more sustainable. So now I want to demonstrate this one for a study that we conducted to look at groundwater remediation. The groundwater was contaminated with PFAS. So it's very important for you to know PFAS. This is the hot topic right now. in terms of the research, in terms of importance. So if you are looking for a research topic to pursue, this would be the topic I would recommend. So what is PFAS, right? So PFAS is short form for per and polyfluoroalkyl substances. So that's the PFAS. And what are these substances? So for example, this is hydrocarbon. You see octane, right? You have carbons and you have hydrogen. But in case of PFAS, you have these hydrogen is replaced by chlorine. So these are all organic compounds, right? And these are all man-made. Hydrogen is replaced by, and then now you have a fluorinated carbon chain. And then you have hydrogen is replaced by fluorine, and then they also have this functional group attached. For example, this one is carboxylic acid. So these have chained structures. So this part is called head and tail. So this is the head and this is a tail structure. So what we're talking about is perfluorinated means all the hydrogens are replaced with fluorine, and depending upon what kind of functional group that you have, based on that you have a you call it for example this one perfluorooctane carboxylate, right? So this is one type of functional group. You could have this and these are the same, but the functional group is different. So here you have a sulfonic acid. So then you get different type of PFAS, and here is known as PFOA, and this is known as PFOS. Then you could have alcohol type PFAS. So it's OH is connected here, all right? So the problem with these things is that you could have many combinations. So you could have carbon chain length, right? So how many carbons that you have, right? You can imagine the permutation combinations, and then what kind of a functional group that you could have, right? How many hydrogens are replaced with fluorine, right? So just think about permutations and combinations. This carbon chain length, it could be 3, 4, 5, 6, 7, 8, 9. You could keep on having those carbon chains, and look at what is this functional group combinations, and then how many these hydrogens have been substituted with the fluorine, right? So that you can imagine how many combinations. Some people say now we have more than 7,000, but in literature you find having more than 4,500 PFAS detected. So depending upon how much, what is the chain length and the functional groups, you will have a unique chemical and physical properties. So here we're talking PFAS is not one chemical. So we are talking about thousands of chemicals with this different unique um, chemical properties and physical properties. So in the literature, they say, short chain PFAS and long chain PFAS. So generally short chain means, when you have a carbons less than 6. If you have less than 6 carbons, then it's called short chain PFAS. If you have more than 6 carbons, 6 or more, then it is called long chain. So you will see the behavior of the short chain PFAS and long chain PFAS, are found to be a bit different. So these are all, as I said, man-made organic compounds, and these have a very interesting properties. They are repellent to oil and water. So oil and water does not stick to it. So a lot of food industries, they use this to wrap their food, and these are also more resistant to friction, and they don't degrade, and they are also resistant to fire, right? So because of these unique characteristics, these chemicals have been used extensively in consumer and industrial applications, right? For example, to create surfactants, resins, molds, plastics, coatings, and more importantly, whenever you have a fire, so whenever you have this fire truck coming and they're spraying, right? So that has the uh, AFFF, so aqueous film forming foam. So that is used to suppress the fires, and that has all this PFAS in there, right? So and because of these unique characteristics, as I said, they are used in many consumer products also. Like they are in the carpets, they are in the paper, they are in non-stick cookware. Nowadays, you see that one because the PFAS has become really a big issue from environmental health point of view, public health point of view. You see now, when you go buy this non-stick cookware, on cookwares, you say no PFAS. They mentioned that. So you should be buying the one that says no PFAS. And then shampoos, and jackets, they are like a waterproof jackets. You get excited, oh, I'm going to buy a waterproof jacket. But why is it waterproof? Because they used PFAS in that. So semiconductor, firefighting foam, metal plates. So many products have PFAS. So even I was telling you, for food delivery, when you go there, the wrap that they use, has a PFAS. So these have been extensively used. So they have been in the society for they have been existing extensively. So the main sources of release into the environment. So fire training, fire response sites, as I mentioned, that has it. So you're basically spreading that. Industrial sites, landfills and dump sites. If you take all the stuff that you used that has a PFAS in the waste, and then you put it in the landfill, and they could leach out, and then leachate could be contaminated. And biosolids, wastewater treatment plants, they found to have the PFAS. So kind of showing the schematically, how you could have these firefighting foam applications, and then you have PFAS that could leach into the soil and into the groundwater. You could have a surface water or sediment. Then from there you could have a leaching. So you have many sources that could be causing the PFAS entering into the subsoils or groundwater. And if you have a nearby water source or groundwater as a drinking water source, having contamination in that means, there's a risk to public health and also to the surrounding environment. So these PFAS are shown to be extremely bad for your health and also to the environment. And there's more and more research that is showing that these PFAS cause cancer. That's why there is tremendous concern by US EPA. Nowadays, they are even finding it in drinking water sources, and even some places drinking water. So now there's serious effort in controlling the PFAS in drinking water. So it has a huge health impacts, and it has impacts on animals too. So because of this serious concern, US EPA is proposing very low maximum contaminant levels, MCLs, of 4 trillions per what is that, nanogram per liter. So that's trillion parts TPP. So that's level that they're considering for drinking water. So there was until recently it's only it was 70 nanograms per liter, but now there's a proposal right now to reduce these concentrations to 4 nanograms per liter. That means the treatment standards have to be improved for drinking water, and there's a lot of research that needs to be done um, to reduce the concentrations to so low values. This is extremely low value. So a lot of different types of treatment and remediation technologies are needed to reduce the concentrations to this level. And if you can reduce to that level, that will reduce the risk. So with that, PFAS background, we looked at one study um, where the groundwater was contaminated, and how do we clean it up? So this is a site in Michigan, in Brighton. The population of this place is only 7,649, and the gallons per capita per day is 100 gallons. They use it. So total water consumption in that city is 800 gallons per day. So this is kind of shows the location of it. It's in Michigan. We are talking about this Brighton, this location. This is the close-up view of that city. And so the source of the contamination is this. So this is the company. This the company name is March Coating Incorporated. It is permanently shut down, and on their website they were saying these things. So I took right from their website when it was existing. So they specialize in the application of paint coatings onto metal substrates for the automobile industry, and they operate 70,000 square feet with an experienced staff of 50 plus employees. Their e-coating services, you can see lists all these things, e-coating paint systems using PPG materials, small samplings to large welded assemblies. So this also wet spray painting services. So all of these, things have a PFAS in them, and they were reusing all their things, and then with improper handling of all their waste and other things. So the groundwater is contaminated with the PFAS. So they were using it at the site. So basically it could be the leaks, or it could be the accidental spills. So that, infiltrated into the ground, and groundwater is contaminated. So they put a groundwater wells. So this is the plan view. So I was showing you the picture of the photograph. This is the building that was there. And these are all the monitoring wells. They put the monitoring wells and then collected the water samples. They measured the contaminant concentrations. As you see here, they found a lot of PFAS in this one. So PFOA concentration maximum was 0.13 microgram per liter. Remember, the limit is nanogram per liter. So PFAS is 2.9 microgram per liter. So the concentrations of this PFAS in terms of PFOA or PFOS are very high. So this, this needs to be cleaned up. So the treatment criteria, basically from these concentrations that you have, there's 0.13, 2.9, you need to reduce those concentrations to these levels, 8 nanograms per liter and 16 nanograms per liter treatment criteria. Generally, you do the risk assessment and define these levels. The one which I mentioned, that's for drinking water levels, so for 4 nanograms per liter. So they have been drawing this much of 800,000 gallons per day during the 1 year period. Um, so the question is, how do we treat the groundwater? So there are not many, good technologies. So the problem with this PFAS is they don't biodegrade. First thing, right? So and depending upon which PFAS you're talking about, they may not be easily uh, oxidized or reduced. May not be may not be suitable for uh, conventional treatment. So one that is being used is basically absorption technique, absorption-based treatment processes. And then you think about what adsorbent that is to use. So commonly they use GAC, granular activated carbon, or ion exchange resin. So basically, you pump it out and then run through this filter that has the GAC or ion exchange, and basically you're absorbing onto that, and then the clean water, you have it, you can discharge into the groundwater or use it for whatever the purpose you may at the site. So the proposed treatment process is like this. So you have a granular activated filter here, you go through certain pre-processes, and then the water comes into this GAC unit, and then you have a clean water. So the granular activated carbon units look like, the filter units look like this, as you see here. And then the one which commercially available shows the average capacity of 189 milligrams PFAS per gram of GAC, right? So this is how we design it. So the one unit. So these are the details about that one. What is the diameter? How much hydraulic loading rate is? So basically, the water goes through this and then goes through the granular activated carbon, and then you have the clean water that's coming out. So the other option is ion exchange resins. So the ion exchange resins, the treatment process is shown here. Again, there are commercially available ion exchange resins. In this case, we looked at IRA 67, IRA 910, and they have a high capacity, 1,300 milligrams per PFAS per gram. And these look like this one. So these are the units. Now the question is, both of them have capability to remove the contamination, right? So, but which one is more sustainable? Which adsorbent treatment is sustainable? So we applied that framework. So first we had to do the environmental sustainability, economic sustainability, social sustainability, and integrate all of them and calculate the sustainability index and provide the recommendation. For environmental sustainability, we use the life cycle assessment, LCA, ISO 14040, as I mentioned. You have this goal and scope, inventory, impact, and interpretation. And then you have to define what life cycle stages you have used, assembly, raw materials, operation, transportation, and the waste management, right? So when you do the LCA, these are the results that you get. So this ozone depletion, global warming, smog, acidification, the ones which are shown on the horizontal axis are the environmental impacts. And it's kind of a relative one to the other, how much is the impact. So you don't see one being consistently better. So for example, GAC is coming out to be bad in many cases, except ozone depletion and fossil fuel depletion. But you see that in general, if you look at all the environmental impacts, the resin is showing the lower impacts related to the GAC gap. And out of all the impacts, carcinogens and ecotoxicity are important. So we quantified the environmental impacts. Then we looked at economic impacts. So you have a direct cost, add-on cost, maintenance and monitoring costs, indirect costs here, and then indirect costs or monetized social costs are also included in this one. So if you do, the detailed calculations for these things, the GAC system versus resin system. So here are the costs breakdown, and the total cost for GSE is higher than the resin. So you have all the cost elements involved. Then looking at the social aspects, which one would be socially acceptable or socially beneficial, right? So for this one, as I said, we use the social sustainability evaluation matrix. We look at how an individual, how a community, how community's environmental and economic situation is going to be affected by this one. So this is done by using a survey, stakeholder survey, and you ask those questions, get the responses. No remedy is not acceptable, of course, because it's groundwater is contaminated and posing problems to public health and the environment. So out of these two, sometimes, when you do the stakeholder survey, they're not technically savvy. So here they're showing that GSC is slightly better than resin from the point of view of the stakeholders. So this is a survey. You create the questionnaire and then ask them to rate those questions. So the GSE had higher points, and compared to the resin, and no treatment had the lowest points. So overall, we have these environmental impacts and economic impacts and social or economic environmental indicators here, and environmental indicators, economic indicators, and social indicators. And so this is what I was combining all the life cycle stages that we looked at it. You can also look at these things per life cycle stage, but we combined all of them and looking at all those things here. And then what is the weighing factor that you have? So if you don't have any reason to give different ones, you can assume equal weightages. But if you can justify, you can use the different weighing factors. So we have all the values, and we have these weighing factors. And then, going through that framework I mentioned, you can calculate the sustainability index. And here is the sustainability index. I mean, you have environmental, economic, and socially combining all of them. So overall, considering the environmental, economic, and social aspects, this resin system is coming out to be better. So, you can see how much better, right? This quantitative framework will help you understand. So let's say this is 0.3, this would be 0.5. So it's like substantial, improvement by using the resin. So here, assuming the environmental, economic, and social are same. But if I want to do some sensitivity analysis, and let's say, hey, social aspects are more important, if I do that one, then, again, resin is coming up better. And then if I weigh, economic factors more, again, my resin is coming out to be better. So even if I do this sensitivity analysis, my conclusion holds. So based on this study, the groundwater treatment using resin adsorbent is the best option. So that's the recommendation. Environmental assessment shows that resin is more reasonable than GSE. Economic assessment shows cost of implementing resin is lower, and social assessment shows slightly favorable towards the GSE. But overall integrated assessment, considering all of them, shows that the resin is the more sustainable method compared to the GSE method. So as I said, I want you to look at this paper where we discussed about this case study and applying the entire framework. So in closing, so it's nice to look at this life cycle sustainability assessment as the framework to assess the options that you have, and then you can select the most sustainable option. And so LCA is the most commonly used tool for environmental sustainability, but tools to assess life cycle economic and social sustainability are not yet fully developed. So there's a lot of research is going on that one. But as I come back to my initial statement, we need to be worried about sustainability, and the sustainable design may not be the requirement right now, but all of us have to, I told you like why we need to worry about sustainability. So it's our moral responsibility to consider the sustainability in every project and do the projects right, and do the right projects and do them right. So also I just also use this not just talk, but quantify sustainability and promote sustainable engineering. So just a lot of times people argue that their system is sustainable without having any quantitative sustainability analytics. So it's better to do this kind of assessment and demonstrate how sustainable it is. And you can make a rational decision on choosing the sustainable option. So if you are interested in learning more about sustainable engineering, this is the textbook that we wrote. Claudio is in the audience, who is one of the co-authors. We use this one as a textbook for teaching the sustainable engineering course in a graduate level. Irrespective, get hold of this book and read it. You will have a broader understanding of sustainable engineering, metrics, tools, and how to quantify and apply and best practices for sustainable engineering, and some examples. So with that one, so this is my contact information. If you need any additional details on this presentation or anything else, let me know. Just to conclude again, it's very important to consider the sustainability, and we need to quantify the sustainability. And there are a lot of problems in geoenvironmental engineering that needs solutions. As I said, soil contamination, the PFAS contamination is one big issue. It could be in the drinking water, or in the soil, or in the groundwater. And we have very low target levels. So you need very innovative technologies. And as I said, PFAS is not easy. All the biodegradation methods don't work. So you need to use the physical, chemical, thermal, electrical methods. So some of these combinations that can work for PFAS. So it's quite challenging problem in terms of the research. So working on these kind of problems is, if you develop a remediation technique for PFAS, you are contributing significantly to the human welfare and also to protect the environment. So doing those kind of projects is very, very important. So with that one, I want to stop sharing and take in